Hello and welcome. I'm Afzal, and today I'm going to talk about the dimensional analysis tool which I recently developed. You can download this tool executable from the link given in the description, and if you face any problem, you can send me an email at mashadab@utexas.edu. Today we are going to do some dimensional analysis on the initial stage of nuclear explosion. In this problem, there is gas motion which arises from the instantaneous release of energy, a finite amount of energy at the center. Initially, the gas in the surrounding is at rest. The pressure is zero, although it's not zero, but it is negligible compared to what we have inside the shock wave or the blast wave. The initial density is rho naught in the surroundings. And in this problem, you have 5 governing parameters, and their corresponding dimensions are given in this square brackets on the side. First is time, dimension t, energy, E, which dimensions ml2t minus 2, initial density ml minus 3, radius, dimension L, and the specific heat ratio of the gas, which is dimensionless. And let me fire off the tool to do some initial dimension analysis. And if you run the tool, which is an executable, you'll get to see this tool window where you have variable name on the leftmost side, and then you have the symbol, whichever you want to assign. And then there is this dimension matrix, and you have mass, length, time, temperature, current, luminous intensity, and the number of moles. If you have any dependent variable, you can just pick any. And there is a tab for calculating the repeating variables, and then you can pick the repeating variables accordingly. In our problem, we have time, and with dimension 1, we have energy with dimension ml2 t minus 2. We have radius with dimension L. We have initial density rho naught with dimension ml minus 3, and then we have the specific heat ratio of the gas, gamma, and it is dimensionless. In our problem, we don't have any dependent variable, so we can just leave it for now, and we can calculate how many repeating variables we need, which is basically the dimension, the rank of this dimension matrix, and it comes out to be 3. And at the same time, you'll see that everything has been filled with 0, and you have these dummy variables dv. Just make sure that if the variable is not being used in your system, you can just use the symbol dv, which just ignores that variable. In our case, we will choose time, energy, and initial density as the repeating variables. And since we don't have the dependent variable in this first problem, we'll have it in the next slide, but for first problem, we don't have it. So here we can just pick a dummy variable for the dimension analysis and just click calculate. And here you'll find the relationship where you have this dv, you can disregard dv, so you can just disregard this term. And then you have the functional phi, which is a function of r over t raised to the power minus t raised to the power 0.4 and e raised to the power 0.2 and rho naught raised to the power minus 0.2. And you have gamma over t raised to the power 0, e raised to the power 0, and rho naught raised to the power 0, because gamma is just dimensionless. And if you do the calculation by hand, you'll find that the pi groups are these, which is r over e raised to the power 0.2, t raised to the power 0.4 over rho naught raised to the power minus 0.2. And pi 2 is just gamma. So this works for the first case. But now we want to know the dynamics of the velocity, the evolution of velocity, the evolution of pressure, and the evolution of density with time. And for that, we have to do another dimensional analysis with governing parameters and their dimensions as follows: time, t, radius, r, with dimension L, initial density, rho naught, ml minus 3 is the dimension. And you have these pi1 and pi2 non-dimensional groups. So this is what you have right now. Okay, and here the dependent parameters are pressure, density, and velocity. And after we perform this dimension analysis, you can either just plot them on the x and y or z axis, and you can see the relation between them, or you can just put them in some PDE if you have it. And if you're lucky and the problem is self-similar, it just beautifully transforms into a nice ODE, which you can solve using MATLAB, or you can also just do it by hand if you're really, really lucky. And let's fire off the tool again, and let's do some dimension analysis again. So let me clear this first, and then type the variable name, time, symbol is t, and dimension is just 1. And then radius, dimension is L, and then you have initial density, dimension is rho naught, and it is ml minus 3. And then you have pi group, pi1, its symbol is just, let's say it's pi1, and then you have pi2, its symbol can be taken as pi2. And here the repeating variables are time, radius, and density. And we also need to have a dependent variable for this case. So dependent variable for the first case can be just density, rho, and this is ml minus 3. And if you just pick it and you do this find the repeating variables 3, we have 3 checks, and here this is the dependent variable density. And if you do calculate, you have rho over this is, you can disregard this small number, this is at machine precision, and you have rho over rho naught equals phi as a function of pi1 over this non-dimensional term, and pi2 over this non-dimensional term. And this is your relation for rho. You can change it to velocity, v, and we know velocity is L t minus 1. And if you do calculate again, you can just find that relationship to be v over r divided by t, and it is equal to phi, which is again a function of pi1 and pi2. And you can do that for pressure as well. And pressure is force upon area. Force is mlt minus 2, and this is ml minus 1 t minus 2. And if you do that again, you have pressure over r squared, rho naught divided by t squared is equal to phi of pi1 and pi2. This phi is different for the different variables, of course, and these are the parameter names if you want to have a look at them. Also, one more thing to show is if you have, say, by any means, you have some linearly dependent repeating variables, say this is time and this is radius, by mistake or by just lack of judgment, if we have same dimensions, or if the basis or the repeating variables are not linearly independent in dimensions, you'll get an error that the repeating variables are not linearly independent. So just make sure that your variables are repeating variables are linearly dependent, otherwise you'll get this error. And we do calculate, you just get this. And let me go back to the presentation. And these are the relations which we found. And these are what you can also find in the book, Berenblatt's scaling book. And the references for this short video are given in here. And you can just go ahead and have a look at that. Get started if you're a person who likes to do non-dimensional analysis, and if you want to see your problem from a different angle. Thank you so much for watching. Take care. Bye-bye.